So double integrals in polar coordinates are also fairly common. They're really nice to do when you have a base region that you're integrating over that is radially symmetric in some way. And sometimes the f of x, y also, if you exchange x and y for r cosine theta, r sine theta, can simplify a lot. So it would be nice if we could translate double integrals from Cartesian to polar coordinates. And one thing to watch out for right now is r should be greater than or equal to 0. It gets pretty confusing. If r is ever negative, well, that'll be the next chalkboard. But just assume for now that r is greater than or equal to 0 all the time. All right, so in this case, let's think about trying to take this base region, which is really nice. It's a ring. So the inner radius is 1, the outer radius is 3, and theta is going from pi over 8 to 3 pi over 8, and that's going to be our region r that we want to integrate over with this function f of x, y. Well, okay, you could just, exchange the x's and y's with r cosine theta, r sine theta, but that's not going to be quite right. Well, let's just, for now, I'm going to write out a little room there, at f. Okay, well, if going from Cartesian to polar, I have x is r cosine of theta, comma r sine of theta. Okay, and then I've got dr d theta, whatever. But let's worry about the bounds for a sec. So the r bounds would be 1 to 3. Let me just put 1 to 3. And the theta bounds would be pi over 8 to 3 pi over 8. Ideally. Okay. But now I've got the problem, right? U substitution in single variable calculus, right? You usually had to, you exchanged x with a bunch of u's, and then you also had to change the dx into usually something times du. But if I just, and that's the same thing here, except it's worse, because you're doing kind of two variables at once. So if I were to just write dr d theta without any scaling factor, without whatever is supposed to be multiplied there, these are not going to be equal. The reason for that, right, is if you do u substitution, so let's say instead I had, I had y equals f of x, I had an integral, of f of x dx, and I changed that into something with u. So normally, right, if this is the x-axis, then you do, delta x, delta x, delta x, delta x over and over again. If you change that into du, I'm going to have to squeeze this in, right, if I changed it, then, that could change the spacing of all these little intervals. So, the first one might get really long, then they might get, a little shorter, bunch up together. You have to keep track of how much you're deforming the x-axis to fit onto the u-axis. And that's what that scaling factor did when you did u substitution in single variable calculus. This is worse, though, because now you're trying to do u substitution essentially with two variables at once, right? So you're exchanging x and y with r cosine theta, r sine theta all at once. So the normal way to do this is with the Jacobian, but that's a little more complicated. Because this is polar, though, there's actually a geometric way to derive it. So now we're going to try something out. So I have to take this to see what you're seeing. So you should be seeing an image on the board from the website. So on the left, you've got the region in Cartesian. And so you've got this ring, and then I've done a bunch of dashed lines, and I have delta r, delta theta, to show a particular wedge of that region. But then on the right, I have essentially theta and r interpreted kind of in a rectangular grid, as if it were Cartesian. So the reason for that is in this integral, the double integral doesn't know anything about what these variables mean at all. It doesn't know they're polar, doesn't know they're Cartesian, they're just variables. And the way every single double integral works is it's going to interpret kind of its integrand, it's integrating, as if it's integrating a bunch of little blocks, a bunch of little rectangles, a bunch of little squares, whatever. And those rectangles have width and height, delta r, delta theta. You shrink it down, they become dr d theta. Now, kind of like in u substitution, when kind of the x-axis can get deformed, where different x intervals got mapped to different lengths, shrunk or compressed to in the u substitution, in this case you have this little wedge on the left is being mapped to a square on the right. And the area of this wedge is not the area of the square. So we need some sort of scaling factor to make sure that when a wedge on the left is translated to a square on the right, that they still come out with the same area. We need that scaling factor, something times dr d theta, to get this to all work out. All right, so that's what we're going to do. So because this polar is fairly simple transformation, it's not some one that I just made up, we can actually figure this out. So now let me go. So if I have, and this is x and this is y, so I've got some wedge somewhere. I'm kind of emphasizing here how much curve there is to the wedge. All right, and so this is going to be my delta r, and this is going to be my delta theta. All right, and I want to figure out what is the area of this wedge. Well, that's not as bad as it sounds. So let's go ahead and take the middle here. So this point in the middle is going to be r theta. All right. And then over here, right, I have the theta axis, I have the r axis. And that wedge is being translated into a rectangle. And I gotta be careful here. So the rectangle has delta theta and delta r. So we know how to find the area of this rectangle, right? It's delta r times delta theta. What about the area of this wedge? We want to scale, we want to make sure we multiply the area of this by a scaling factor to make sure it still ends up as the area of this wedge. Well, one way to do that is to calculate the area of the wedge. So in here, right, this is a ring, so, and I might have enough room, sort of. All right, so it's a ring. It's a piece of a ring. So here we go, we have a round. So the first thing is, okay, what's the area of the entire ring? Well, to calculate that, I have my r theta right there in the middle, and I should do that over here as well. R comma theta point. And to do that, I'm going to take the area of the outer circle, I'm going to subtract the area of the inner circle, and that's going to give me the area of this ring, right? All right, well, so the ring area. Okay, well, let's see. I've got the outer circle. That's going to have pi times the radius squared. So I've got pi times, it's r plus delta r over 2. Right, because if the entire length here is delta r, and I go, this is in the middle, then from here to up there, it's this half delta r over 2. And then that's squared, right? So I have pi times the radius squared is the area of the outer circle. I'm going to subtract from that the area of the inner circle, which is pi times the inner radius squared. Well, that's going to be r minus delta r over 2. We went back, towards the origin a little bit. So r minus delta r over 2 squared. Right, and if we simplify that a tad, let's see, so pi times r squared. Okay, so this one times 2. It's going to be r plus r times delta r plus, okay, this one's squared, so delta r squared over 4, yeah, minus pi times, okay, r. In the middle now we'll have a minus r, delta r, just delta r. And then, let's see, yeah, and then plus pi, delta r squared over 4. Delta. Okay, and if we simplify that, well, here I have pi r squared, and here I have minus pi r squared, excuse me. So those are gone. All right. But but I also have a pi times delta r squared over 4 minus pi times delta r squared over 4. So those are gone. So I actually only have the middle pieces left. I have pi times r delta r minus pi times negative r delta r. So this actually all simplifies. Right, that canceled, that canceled. It goes down to 2 pi r delta r. All right, well that's the area of the ring. Now if I want the area of just this wedge, then I can actually just take it as a fraction of the area of the ring. All right, so then the fraction of the area of the ring, right, this delta theta, to get a fraction, right, if I divide delta theta by 2 pi essentially. So the wedge area that's going to be the ring area times the fraction of the ring. All right, well the ring area is 2 pi r delta r. And then the fraction of the ring, well the entire ring, all the radians, that would be 2 pi, but I only have delta theta of those radians. So the whole fraction is delta theta over 2 pi. So we multiply that, the 2 pi's cancel, and then we end up with r delta theta. So it looks like, right, delta r delta theta, that's the area of this rectangle over here, because the double integral is interpreting r and theta in a rectangular coordinate system. But we want to make sure, this wedge really had area r times delta r delta theta. So it looks like our scaling factor is really just that r there. And that's what it is. All right? So whenever I take a wedge over here and I translate it into this coordinate system, I need to make sure I multiply that wedge by r in order to get the area, I need to multiply this square, this rectangle, by r in order to get the same area as over here. All right? Intuitively, the reason that works out is if I'm closer in here and I have the same delta r, I have the same delta theta, this is a much smaller wedge. The r is the same, but delta theta kind of shrunk it down more. Versus if I'm way out here, I kind of did that right. Right, delta theta actually had a bigger impact on making it longer, and delta r. And those are supposed to be the same length, whatever. So that's what the r is scaling. The further away this wedge is from the origin, kind of the delta theta is actually stretching out more and more. So to compensate for that, because this square right here, and this square right here, this wedge right here, and this wedge right here, and this wedge right here, all end up being the same square size over here. To compensate that the wedges are actually getting bigger the further away from the origin you are, meaning the bigger that r is, then we're going to say, okay, well, to make sure that you get the same area here and here, we're going to multiply this area by r. All right, so then this was not equal, but if I had changed it just a little bit, so I'm going to get rid of my not equals there. If I had changed this just a little bit, and instead I have my r times dr d theta, then they actually are equal. So this is the super duper fancy scaling factor that is kind of like a U substitution in polar coordinates. All right, so you can do this translation from a nice region that is radially symmetric in some way, from Cartesian to polar, as long as you exchange the dx dy with r dr d theta, or equivalently r d theta dr, right? Just making sure the intervals match the order. That will work. So now the last thing is, okay, well, what happens when r is less than 0? The reason r less than 0 is a problem is, right, so in single variable calculus, right, if you went below the horizontal axis, it got interpreted as a negative area. So if r is ever negative, when you're doing this integral, it can end up causing negative base areas. So we'll do an example and also how to avoid that. One final thing before moving on, double integrals in polar, we can actually check this result if f of x comma y equals 1, and we can actually check these intervals are equal just using geometry. We don't have to actually do any integration. So if f of x comma y equals 1, then our region R is this wedge again, and it's between theta is pi over 8 and 3 pi over 8, and R is between 1 and 3. And so here this integral, setting up the bounds, would be actually quite terrible, but it's just a 1 times dx dy. And over here, when you do the change, you get nice bounds, and it's 1 times r dr d theta. All right, so I'm not good at drawing, so there should be an overlay now of the 3D images of these things. So the left one is the wedge, and it's been raised up vertically in the z-axis, a little bit, and we want to compute the volume underneath that surface, underneath the wedge, type 1. But then on the other side, that's the interpretation of the double integral here, interpreting r and theta as the horizontal and vertical axes, and it's actually integrating over a rectangle. And then its height is a little weird though. It ends up making, when it's increasing in r, it's got that slanted plane. And those aren't that difficult. So this is a wedge of a circle with height 1. We can calculate the area of the wedge multiplied by 1 to get the volume. And the other one is a trapezoidal prism, or whatever it's called. So for the left one, let's go ahead and do that. So to get the entire volume of underneath that shape, I'm going to take the wedge area, and I'm going to multiply it by the height. All right, well, the wedge area, I don't usually do fractions and fractions, but here we go. It's the fraction of the radians that's gone through. So it's 3 pi over 8 minus pi over 8. Right, theta goes from pi over 8 to 3 pi over 8. I need that total radians. And then it's the fraction of the entire radians of an entire rotation, so that's 2 pi. And then I'm going to multiply that, so that's the fraction. I need the area of a ring, and that ring has radius 1 on the inner diameter, inner radius, and then radius 3 on the outside, outer radius. And I need the area, so I'm going to take the area of a circle of radius 3, so that's going to be pi r squared, so pi times 3 squared, minus the inner circle, which is pi times 1 squared, then times the height, which is 1. Now we get to simplify these lovely fractions. So here we go. I'm going to change this to not be fractions and fractions, so I have 1 over 2 pi. And here, so that's going to be the numerator. So I have 3 pi over 8 minus pi over 8. That ends up being 2 pi over 8. That's the same as pi over 4. Okay. And then times, this is 9 pi minus pi, so that ends up being 8 pi. And then times 1. That ends up equaling pi. The area, the volume under the wedge with height 1 is pi. We do the same thing for the trapezoidal prism, or whatever that thing's called. Well, all right, so you have I'm going to take the base, so the theta part. It's the range in theta. So I've got the length. Oh, come on. Times the trapezoid area on the end. Okay, well, the length, that's 3 pi over 8 minus pi over 8. Then the trapezoid area, well, that is going to be, so over here, our trapezoid. All right, this is at r equals 1. This is r equals 3. And this has height of 1. Right, because the z, it's height 1 there. Z equals r. Then over here, it has height 3. Oh, sorry, it's supposed to be a 3. So then to get the area of a trapezoid, first it's going to be the base. So that's 3 minus 1 is our base, right? Down there. And then to get the height, right, the equivalent height, and it's the base times the average of the height. So I'm going to take 3 plus 1 over 2. All right, that's equivalent to kind of taking this triangle and moving it over there. All right, if you flip it over, it'll have height 2. All right, so if we simplify that, 3 pi over 8 minus pi over 8, that's 2 pi over 8. Again, that's pi over 4. Okay, 3 minus 1, that's 2. And this is 4 over 2, so that's 2 again. And that simplifies to pi. So yeah, they end up being equal. So somehow there's some way to cut up that wedge with height 1 and rearrange it into that trapezoidal prism. Now to follow up on that warning I gave for r greater than or equal to 0, okay, well what happens when r of theta is less than 0? So here's the example. So again, can't draw, so there should be some overlays there. So we're integrating over this region r. So this is a circle, and that's 1 right there. It's a radius 1/2 circle, centered at x is 1/2, y is 0. All right, so that's our region. And then we're integrating a cone. So this ends up being a cone. It's a square root of x squared plus y squared dx dy over that region r. And then if you were to translate that, I haven't given these because it's not very pretty, but it's just region r. But if you do translate it into polar, the r and theta can come out nice, but there is a little bit of a problem. So let's take a look at this. So if I take x squared plus y squared, well, x squared plus y squared is actually r squared. So then I get the square root of r squared is r. So that accounts for one of these r's. And then changing dx dy into r dr d theta, you end up with r from the square root of x squared plus y squared times the r from the r dr d theta gets you r squared. So that's the integrand in polar. And then to get to 0 to cosine theta, so unless you remember that the circle centered like this is cosine theta, you know, that's a good way to do it. But if you don't, like I did when I took this course back in undergrad, I actually go through doing the entire problem on the touch screens. There should be a link over there, and that should get you to a playlist that will show you kind of all the work to do these. But just for now, let's pretend that you know it's 0 to cosine. So then the next thing is, okay, well, what should you have the theta bounds be? Well, there's a couple options. So, 0 to pi, that seems pretty nice. If you do trace this out, you start at 0, you end up going this way, and then it traces out the circle with r getting less and less and less until you get to pi over 2. Once you get past pi over 2, you actually start going negative. So then you end up tracing out this part of the circle. You can kind of see that in the graphic down there. The bad thing about that, though, is r ends up being negative. So from 0 to pi over 2, cosine of theta, right, r of theta equals cosine of theta, is positive. But then for theta between pi over 2 and pi, you end up with negative values of r of theta. Cosine of theta, when theta is between pi over 2 and pi, is negative. And so that really messes up evaluating the integral. And if you actually evaluate this integral as is, you get 0. And that's definitely not the volume, right? So you can see on the right side there, like the left, you have the circle and the cone above it. On the right, you have kind of the 3D shape as if you brought the circle up to the cone and then nothing else. Right, that definitely has non-zero volume. So this is wrong. And it's wrong because r was less than 0 for part of the time. And so you ended up kind of getting negative volume. All right, so don't do that. So an alternative is instead, okay, well, if we want to keep r positive the whole time, and we're looking at r of theta equals cosine theta, instead of going from 0 to pi, which kind of did this, so positive, decreasing, r is less and less and less, finally get to pi over 2, you're at 0, and then you have negative, and you go to pi, and you're at negative 1. You could have also done negative pi over 2 to pi over 2. And in the cosine graph over there, you see it's always positive. So we start at negative pi over 2, which is down here, so it starts at 0. And then you start getting closer and closer to 0. You're getting bigger and bigger r values that are positive. You eventually get to r equals 1 when theta equals 0. Then you go around, and now r is increasing towards pi over 2. You still have positive values. When you finally get to pi over 2 for theta, you have r is 0. So that time you actually traced out this entire circle, but r was positive the entire time when you go from negative pi over 2 to pi over 2. And then if you actually evaluate this integral, since r is positive the whole time and you essentially are integrating positive areas, positive volumes, you get the actual answer, which is 4/9, which I find interesting. There's no pi's in it. And if you evaluate this one, do a lot of hard work, you get 4/9. Okay, so this is just, be very careful, watch out. Try as hard as you can to not have r of theta equal to 0 ever. If you do, it can be done, but it's a mess and it's not worth the effort. All right, so, and it's kind of when you do if you have r dr d theta and r is negative, it's almost like negative area. It gets weird. All right, so that is your warning. Try not to do that. If you do want worked out examples here, there's a link in the top right again. And we'll do one more for over a plane. All right, so one more example at the chalkboard. So got our old one here, which used to be up there. That was the cone over this circle. And now we're going to do a plane. So it's essentially the plane z is equal to x over that same circle. And you can also translate that and keep in mind, make sure r is not negative, so 0 to cosine for r, negative pi over 2 to pi over 2 for theta. The reason we got r squared cosine here is the x is equal to r cosine, so that's 1r times cosine, and dx dy turned into r dr d theta. So the r cosine times r dr d theta got you r squared cosine theta dr d theta. All right, and they have similar shapes, so this one actually has a little bit more volume to it. It kind of curves up a little more on the side. This one's been kind of cut off in half. And it's one more example, so we can actually calculate this by hand. So let me go ahead and do that. So because this one has a nice flat top to it, it's actually just half of a cylinder at that height. So if we actually calculate that, it's 1/2 times the volume of a cylinder. Cylinder. Okay, that was sort of legible. All right, so 1/2. So the cylinder is the base times the height. Well, the base of this thing is radius 1/2, so pi r squared. So pi radius squared is radius 1/2 squared. And then times the height, which is 1, right? So when x is equal to 1, that would mean that the height, z, is equal to 1 at the top. Right, and then that evaluates, and then it's been chopped in half. That's what the 1/2 is from. So that ends up being pi over 8. And so both of these, if you actually evaluate the integral, it's pi over 8. Pi over 8 is about, what is that here, 0.3927. Dot, 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 The 4/9 is about 0.4444 dot, dot, dot. So fairly close to each other. But again, this is one more example of the chalkboard. But if you actually want to see these done out completely, you're either already in that playlist, or if you're not, you're just in the list of chalkboard videos. There's a link up there that should get you to that example, and then there's a few more on the touch screen. So we actually go through calculating the integral bounds, actually doing the integrals, evaluating them, all that fun stuff.